Thank you, Neil, and thank you to Gwen for inviting me today. It's a real pleasure to speak to this group. Um, so I am the Education Director for Las Cumbres Observatory, but I am also the President of the IAU Division C, which is Education, Outreach, and Heritage. So I'm sort of here on my job hat on, if you like. Um, So fundamentally, where do we put telescopes as astronomers, as amateur astronomers, professional astronomers, and just people interested in the night sky? Well, a few years ago, I'm based at Cardiff University, which is in Wales, in the middle of the capital city of Cardiff. And I wanted to install an all-sky camera. I happened to have my hands on an all-sky camera. I thought it would be rather nice to have one on the top of the physics building next to our observatory dome. Um, and this is the view that I got at 3:30 in the morning of the sky. Now you'd be forgiven to think that this is a cloudy night. This is not a cloudy night at all. This is a beautifully clear night. And it really shows why there's an observatory dome here that's sort of on the lower left side of this all sky view, and it never opens. And in fact, now it doesn't even have a telescope in it. It is used as a storeroom. There's a light down towards the bottom, almost sort of the center, that you'd be forgiven for thinking was a street light. That's actually the full moon. And if you've got very keen sight, you may spot the odd couple of stars, but light pollution is preventing us from seeing anything in the night sky here. But if we take a telescope or take this all-sky camera up to an astronomical observatory site, you see something more like this. So this is the same camera in an astronomical observatory site. It's actually this site in Hawaii. So you can see that by cleverly putting telescopes in the correct places, then you can get wonderful views of the heavens, the night sky. That's our observatory there, actually. Lots of people say, is it the big silver bucket? But you can imagine that this being at a US site, the big silver bucket is owned by the US Air Force for tracking things that are much closer than stars. Um, but sometimes, well, if you then make your observatories robotic, as this one is, you can see that on the left-hand side, the dome opening and closing as the sky gets clearer, and when the sky gets a bit cloudy, the observatory closes up on this time lapse, and there's a little bit of cloud thinning out there, and then it closes, and that's the full moon that you can see going through the sky there, not the sun. And this is dawn coming here. But sometimes your observatory site will look like this. It'll be, because these are normally sites at altitude, you get sites that are completely fogged out, clouded out, embedded in snow for large periods of time. So if you've invested all of your money in a telescope site and just one of them, and this happens for a large portion of the year, that stops what you can do with it. So at Las Cumbres Observatory, we have a global network of telescopes. And these are all the sites that we have. We have 7 sites and 25 telescopes. But rather unusually, we have 10 telescopes that are our educational network. These are 40 centimeter class telescopes. They're actually not 40 centimeter, they're 35 centimeter delta rows made by plane wave instruments. And you can see I've highlighted in red there. So a lot of them are, all of them are co-located with other telescopes. A lot of them are paired up. And this is our currently operational network of 2 2-meter telescopes, 9, we've actually got more than that now. We've got 13 1-meter telescopes and 10 40 centimeter class telescopes. And these are the new 40 centimeter class telescopes that we replaced all of our original Meads with. Now, because we've got telescopes all over the world that are networked together, that behave robotically, and you can see from these pictures that there's no eyepiece on these telescopes. There is an instrument package. On the 40 centimeters, there's actually just one instrument, which is a camera. But the bigger telescopes, there are more, and they are robotically controlled. And that means that nobody needs to go to the site while these telescopes are operating. Um, and actually, we simplify it even further so that you don't need to schedule observations at a particular telescope. We make it the whole system able to operate as a single scientific instrument where observations are passed from one site to the next all around the night as you want to study an astrophysical phenomenon. And this makes it possible to do something called time domain astronomy or time domain astrophysics. I just realized that I don't. There, you can see me now. My camera was off for some reason. So time domain astronomy, which means that you can follow something in the night sky as it's happening. Not spatial domain where you're moving a telescope around, but you're looking at a single thing happening over a long period of time. And one of the things that we were involved with back in 2017 and continuing now is the follow-up of gravitational wave events. We actually are involved in follow-up of many, many different types of phenomenon that come out of surveys like the Zwicky Transient Factory and the Palomar Transient Factory, and obviously the Rubin telescope, which will generate a huge amount of transients for telescope networks and individual telescopes to follow up on. But gravitational waves was a particularly exciting one that I had a very small part in. And yeah, I'll tell you a little bit about it and how that worked for robotic telescopes. So there was the Fermi telescope saw gamma rays in this portion of the sky. I mean, gamma rays, okay, we see gamma rays quite a lot in different parts of the sky. But this time they were linked with gravitational waves at about the same time, and there was an overlapping area that Fermi saw the gamma rays and LIGO Virgo saw gravitational waves. And this was very exciting because until this point, when gravitational waves, this is a couple of years after gravitational waves had been established to be real things and had been detected. When two black holes collide, you see a burst of gravitational waves, but the optical counterpart to that looks like this. Absolutely nothing. So because there was a burst of gamma rays, which are optical, which are electromagnetic, we knew that this couldn't be two black holes, and it's actually two neutron stars. So this was the air. This is the whole sky. The stretch sort of banana is where we had to look for that, and that little dot is the LCO, the field of view of one of our 1 meter telescopes. It could be just about any of our telescopes because that's the whole sky. So we had to map that huge area. How do you do it? Do you take the whole sky and do you just slap a grid on it and then gradually, go through one by one each bit until you've filled in that whole area? Slip of tea. Well, no, because that would be a terrible waste of time because lots of the bits in between interesting things are blank, empty. So we'd waste a lot of time, and time is of the essence when you have a phenomenon that you're following up on. So we saw a burst of gamma rays, and we knew that it was probably a phenomenon like a supernova, and supernovae occur in galaxies. So instead of just surveying that like a grid, we then said, well, in that area of overlap between these two announcements, let's have a look at the galaxies. And you can see on the little panel on the right, those were all the galaxies that were observed. So we actually observed 30 galaxies in a period of 12 hours. And we didn't have time to analyze them at the time. We just carried on going. This researcher that you can see down there, Arkavi, my colleague Yair Arkavi, did this observing. And he went through just observing these galaxies, chuk, 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 until he found this. And it was only after, it was the fifth one he'd observed on the list, but he didn't have time to stop and analyze them, just carried on observing. This is the before and after picture, catalog image on the left and the LCO image. Woohoo, it was all worth it. The expense, the heartbreak, the time, the sweat and tears. We discovered a kilonova, which is the coalescence of two neutron stars. Well, no, we didn't, because the Swift telescope got there. If you look at the timestamp there, this is 18th of August, 0015. The Swift telescope got there about 42 minutes before. Rats, missed it. But that's not the end of the story, because one of the things that I told you about last Cumbres is that we have a network of telescopes. So what we have here on the bottom is time across the 2 days, the 17th and the 18th. And then you've got altitude, and then the top is hours since merger. So what we're going to do is sort of scan from this first one, the discovery image there, and then we have 3 sites in the southern hemisphere. Now, this object, as you can see, this line shows how high above the horizon, according to those times, that object was, and it set very rapidly. I think it was visible for about 45 minutes before twilight, and so it was, or just after twilight. All the telescopes were frantically trying to get data on this, but we have 3 sites in the southern hemisphere, so we managed to grab snapshots of this 3 times in the time that the Swope telescope was able to observe it, and then observe it 24 hours later. We got 3 data points there. And one of our observatory sites at the time had spectroscopy available. Actually, all of them do now, but just the Australia one did at the time. So as well as follow-up observations, we managed to get spectroscopy, which is extremely important in characterizing this object, because we didn't really know what it was at the time. So there's the 3-color image composite of the kilonova, and as it faded with time, you can see it in the one on the 18th, and it's almost gone by the 23rd, so 5 days later. So that sort of shows you that you really need to get on and observe this very, very quickly. This cartoon graphic shows you also the importance of having multiple sites around the world, because the very first image, the discovery image at Chile, we snapped it, but then the phenomenon was carried on brightening. Now, if we'd only been able to take one observation every 24 hours, we would have missed that peak. And the peak brightness is what you really want to find, because you can align that with scientific models then. So we managed to get 3 observations there, where most other observatories would only be able to get 1. So that's the science that you can do, but how can you be involved in robotic telescopes? We run a program called the Global Sky Partners, and it's our way of creating a sustainable, scalable, high-quality education program using our robotic telescopes. We partner with groups and organizations who provide fully supported educational projects. Some of them are people with amazing track records, and some of them are people who just have a really good support plan for their audience and a really good idea. We don't charge for this. It's entirely free for people to be involved in. But we do have some requirements. One of the main requirements is that we want to make this opportunity available to underserved communities, people who wouldn't normally have this type of opportunity. We'd like them to be innovative, because we think that our network of telescopes is innovative, but they also have to be educational. These are not programs for people to sneak science into for scientists. If educators want to do science with their audience, with their students, that is great. But if you're a wealthy American university, you cannot use this program. Um, in this current cohort, we are running with 37 partner programs from all over the globe. I'll tell you about just a couple of them now. Beyond the Stars is a program running in the Canadian Northern Territories, and it runs in hybrid, so in person and via Zoom. And it was started just as the pandemic was easing, in a very, very remote community, a community which doesn't have any astronomers, doesn't have any real specialists. It has the students that it's targeting are ones with some of the lowest attendance rates to high school in the whole of Canada. It's really a population of young people who are totally disaffected. They are largely unforgotten, and they have very few prospects in their local community. They actually notice that the students quite often go to school having had alcoholic drinks. It shows how bleak their lives can be. But what they found with this program was that they were turning up. The students were actually engaging, and the researcher who was involved in this was talking to me about it and said, I don't know what to do. They look really not happy to be there. I said, you just have to talk to the teacher and see if there's other ways that you can engage them. And when she talked to the teacher, she found out actually that all of the students loved being there. They had record numbers of students attending because somebody cared about them enough to turn up every week. And actually, what she thought was miserable faces was actually them concentrating really hard on what they were doing, which is really quite wonderful. Now, these places are inaccessible by road. They're only accessible by boat or plane. So the researcher went and visited them a couple of times towards the end of 2023. Um, and that really gave a massive boost to that program. So that program has, it's difficult to measure impact with all these programs because they're so different, but this had a really deep impact on a very small number of people. Hmm. The next one is called Deep Sky Images. I won't embarrass myself by attempting to pronounce Portuguese. It's had been called Brazil 1000. And this runs in hybrid as well, in person and uh, through video conferencing. And that's just because Brazil is so large, but also that they want to target rural areas and rural parts of Brazil. It's aimed at teachers without or with little STEM or astronomy experience. And this program has managed to train teachers in all 26 states and the administrative district of Brazil. It's a three-step program. LCO is the first step, so they use our robotic telescopes to have their first experience of using telescopes and doing astronomy. They learn about types of objects. They take an image with LCO. They get a really nice three-color image back, and then they do a small project on it with their students on that object. And then they may stop there and they may just do the same thing each year, or they can take it further. They can be involved in uh, the National Olympiad. They can do asteroid follow-up measurements as well. You can see down in the bottom left, there's a picture, and that's one of the government ministers of Brazil, because this program is endorsed by the Technology and Innovation Ministry. And the minister invited as many teachers as possible to come to Brasilia and receive awards for being involved in this program. And you can see everybody there is either a teacher or a senior student that was involved in this program. Really quite amazing. And the final program out of the many that we've supported over the years is called Mission Platinum. This program ran in India. It has two aspects again, and it was in partnership with the British Foreign Office, Foreign and Commonwealth Office, and it was tied to the British Queen's platinum anniversary. And what they wanted to do was partner with schools. So the British High Commission donated computers to the schools so that they can be involved in a science um, project. And we were very happy to help with that. So uh, there were two phases for the project. Initially, we had 30 teachers involved in taking astronomical pictures. I trained these 30 teachers on a Friday night on how to use a control interface and motivate them about what the project was about and showed them examples of things to do. If I'd done that in the UK, everyone would have gone away. I would have sent a follow-up email a week later. Still nobody would have made any observations. Those 30 teachers took 10,000 astronomical observations over the weekend. So they used their own time at the weekend to completely lock up our dynamic scheduling algorithm with 10,000 observations. Really quite wonderful that they were so enthusiastic about this program. And then they met the British High Commissioner to India. Some of them met and discussed what they did in that project. And then we had a world record attempt at the largest ever astronomy lesson, which we actually managed, although we weren't willing to pay the €7,000 to the Guinness Book of World Records to have it validated. But we had over 7,000 students attend an online astronomy lesson given by Professor Carol Mendel, who was with the European Space Age, the European Southern Observatory at the time. It involved 140 schools from the Bulandshahr Uttar Pradesh state, and yeah, it was really quite an amazing program to be involved with. Every year we have roughly 60,000 direct and indirect people involved in our programs. I'm sorry this graphic is a little bit out of date, but it shows since we started the program in 2018 how these are the number of partners who target audiences in these different geographic regions. And as I said right at the start, one of the aims of this program is to increase the participation of people who are not normally represented in these type of programs. They're people who maybe don't have experience of running programs. There may be people who just don't know about these opportunities. So I've been desperately trying to increase the participation from people from the global south in this program. So that's all I wanted to say. Thank you very much for listening to me. If you want more information about the program, there's the observatory's website, and if you want to know more about me, there's my personal website as well. Thank you.